April 24, 1941. Warren, Michigan. The first M4 Sherman tank rolled off the Detroit Tank Arsenal assembly line with a sound European engineers would have called impossible, the mechanical precision of interchangeable parts clicking into place like clockwork. Through the industrial hum of Michigan factory floors, American ordnance officers were building tanks using methods that contradicted everything European armor doctrine said was necessary for battlefield supremacy. No complex engineering, no irreplaceable components, no specialized repair facilities required. European tank design philosophy demanded thick armor, sophisticated mechanisms, and factory-level maintenance, machines built like fortresses that only master technicians could service. The Germans were perfecting Panthers with advanced torsion bars and precision-engineered final drives that promised devastating firepower. The Americans were building something entirely different: bolt-on nose plates, modular suspension bogies, engine power pack designed to lift out with 4 simple brackets. Major General Barnes had bet America's armored future on one radical idea: a tank you can fix tonight fights again tomorrow. The rest of the world was about to discover why availability beats perfection. Major General Gladian Barnes stood in the cold morning air at Aberdeen Proving Ground in February 1941, watching a prototype M4 Sherman negotiate the test course with methodical precision. The tank weighed 32 tons, 2 tons over his preferred limit, but it moved with the steady reliability that had become his obsession. Barnes had spent the previous 18 months fighting a quiet war inside the U.S. Ordnance Department, a war between two fundamentally different philosophies of what a tank should be. The European approach, refined through decades of continental warfare, emphasized individual superiority. German panzer designers pursued thick armor, sophisticated transmissions, and cutting-edge metallurgy that produced machines like works of art. Each tank was a statement of engineering excellence, demanding specialized tools, factory-trained technicians, and replacement parts manufactured to tolerances that left no room for field improvisation. The French Char B1 and British Matilda followed similar logic, fortress-like vehicles built for elite crews and depot-level maintenance. Barnes had studied those machines during his pre-war intelligence assignments, and he understood their appeal. But he also understood something their designers had missed. Wars were won by tanks that fought tomorrow, not tanks that impressed today. The American specifications that emerged from Barnes's office in late 1940 reflected this philosophy with mathematical precision. Maximum width, 103 inches, the limit for standard railroad flat cars and landing craft. Maximum weight, 30 tons, the capacity of most U.S. bridges, and the practical ceiling for reliable mechanical components under stress. These weren't arbitrary numbers, they were the constraints that would allow American tanks to reach the battlefield and return to fight again. Transportability equals availability, Barnes had written in his September 1940 memo to Chief of Ordnance Major General Charles Wesson. A tank that cannot move to the fight, or cannot be repaired when damaged, contributes nothing to victory regardless of its individual capabilities. The memo had triggered months of heated debate within ordnance circles. Critics pointed to German successes in Poland and France, where heavy Panzer IVs had dominated lighter Allied vehicles through superior firepower and protection. Why build a 30-ton medium when the enemy was fielding 45-ton heavies? Barnes's response was characteristically methodical. He pulled maintenance records from the German campaigns and found that German armored divisions were losing more vehicles to mechanical failures than to enemy action. By December 1940, Barnes had won the philosophical battle and begun the practical work of turning doctrine into steel. The contract for America's new tank arsenal went to Chrysler Corporation, with K.T. Keller overseeing construction of a massive facility in Warren, Michigan. Keller, a foundry mechanic who had risen to corporate leadership, understood both the industrial challenge and Barnes's strategic vision. The Detroit tank arsenal would be designed around the principle of standardized, interchangeable production. Every component manufactured to identical specifications. Every assembly process documented in technical manuals that any trained mechanic could follow. William Knudsen, the Danish-born production genius who had transformed Ford's assembly methods, joined the mobilization effort as director of the Office of Production Management. Knudsen brought systematic thinking to the chaos of military contracting, establishing the parts numbering system that would become standard nomenclature list G104 for the M4 series. Under this system, a transmission bearing in a Sherman built in Detroit would carry the same part number as an identical bearing manufactured in Cleveland, ensuring that maintenance crews from North Africa to the Pacific could order exactly what they needed without confusion or delay. The first production Sherman rolled off the Detroit Arsenal line on April 24, 1941, followed by steady increases in monthly output. By summer 1942, the plant was producing over 300 tanks per month. By December, output peaked at 896 M4s in a single month, a rate that German and British factories, with their emphasis on individual craftsmanship, could not match. Yet even as production accelerated, criticism mounted from unexpected quarters. Armored force officers who had studied German tactics argued that the Sherman's 75mm gun was inadequate against newer Panzer designs. The tank's maximum armor thickness of 76mm compared poorly to the 80 to 100mm protection of German mediums. In technical conferences at Fort Knox and Aberdeen, younger officers pressed for heavier guns, thicker armor, and more sophisticated fire control systems. Barnes listened to these arguments with the patience of an engineer who had run similar calculations dozens of times. The critics were correct about individual vehicle capabilities. A Panzer IV, with its long 75mm gun, could penetrate Sherman armor at longer ranges than the Sherman could reply effectively. But wars were not fought by individual vehicles. They were fought by formations, and formations required logistics. The engineering solution that Barnes and his team developed reflected this systems-level thinking. The Sherman's transmission and final drive were mounted at the front of the hull, behind a bolted armor plate that could be removed with standard wrenches for complete powertrain access. The suspension used vertical volute spring bogies that bolted to the hull on standardized mounting points, allowing entire wheel assemblies to be swapped as modules rather than repaired component by component. Even the turret was designed for rapid replacement. The entire assembly could be lifted off the hull ring and swapped with a crane and 4 men. This was not prestige engineering. It was availability engineering, designed around the assumption that tanks would break down, take damage, and need repair under field conditions by mechanics with ordinary tools and limited time. Every design decision prioritized speed of service over sophistication of mechanism. Every component specification balanced performance against the probability that replacement parts would be manufactured by different contractors in different cities under wartime stress. The rule that governed every choice was simple. If a farm mechanic with a technical manual could not repair it in a field workshop, it did not belong on an American tank. By late 1942, this philosophy was producing results that surprised even Barnes. American armored divisions in North Africa were maintaining higher operational readiness rates than their German opponents, despite facing supposedly superior equipment. The difference was not in individual vehicle quality, it was in the systematic coordination of design, production, and maintenance that kept American tanks fighting, while German vehicles awaited specialized parts and factory-trained technicians. The Americans had chosen availability over prestige, and the choice was beginning to matter. Charles Sorensen walked the Ford Rouge complex assembly floor in March 1943, watching workers install the final components of his 1,000th M4 power plant. The 18-liter Ford GAA V8 engine represented everything Sorensen had learned about mass production during 2 decades of automotive manufacturing, adapted now for the demands of armored warfare. Each engine was assembled to identical specifications using interchangeable parts manufactured at Ford facilities across Michigan, Ohio, and California. The result was a power plant that any Sherman crew could service using standard automotive tools and documented procedures. The GAA mounted to the Sherman's hull through 4 precisely machined brackets, each secured with grade 8 bolts that carried the same thread pitch and torque specifications, regardless of which Ford plant had manufactured them. Sorensen had insisted on this standardization after studying early Sherman field reports from North Africa. where crews had struggled to repair tanks using mixed components from different contractors. Under the new system, a transmission removed from a Detroit Arsenal Sherman would bolt directly to an engine manufactured at Ford's Dearborn plant, eliminating the custom fitting that had plagued earlier production runs. By summer 1943, this standardization had expanded across the entire M4 supply chain. Press Steel Car Company in Pennsylvania manufactured hull plates to specifications that matched exactly with turrets produced by Pacific Car and Foundry in Washington State. Fisher Body Division stamped track assemblies in Cleveland using the same tooling patterns that guided production at American Locomotive Company in Schenectady. The result was true interchangeability. Any Sherman component could be replaced with an identical part from any authorized contractor, creating a maintenance system that functioned like a giant standardized toolkit. K.T. Keller had driven this integration from his headquarters at the Detroit Tank Arsenal, where monthly production had stabilized at over 700 vehicles by late 1943. Keller understood that building tanks was only half the challenge. The other half was ensuring that those tanks could be maintained in the field by crews with limited training and basic equipment. His solution was comprehensive documentation that translated complex mechanical procedures into step-by-step instructions any literate mechanic could follow. Technical Manual 9-759, published in August 1943, contained detailed maintenance procedures for every major Sherman component. The manual's section on power plant removal specified exact bolt torques, lifting procedures, and safety precautions in language that assumed no specialized knowledge beyond basic mechanical principles. Page 112 showed crews how to disconnect the clutch assembly using a standard socket set. Page 115 illustrated the proper technique for lifting the complete engine transmission unit using the 4 factory-installed lifting eyes. Page 118 provided troubleshooting charts that diagnosed common problems through simple visual inspections. The manual's approach reflected Barnes's original philosophy, translated into practical terms. Complex mechanical systems were broken down into modular assemblies that could be diagnosed, removed, and replaced as complete units. A crew experiencing transmission problems did not need to rebuild gear sets in the field. They removed the entire transmission module and installed a replacement from depot stocks. The faulty unit was shipped back to specialized facilities where it could be rebuilt using proper tooling and quality controls. This modular approach extended to the Sherman's suspension system, where Barnes had specified vertical volute spring bogies that mounted to the hull through standardized attachment points. Each bogie assembly weighed approximately 400 pounds and could be removed using a field crane and basic hand tools. The technical manual provided clear illustrations showing the 12-bolt pattern that secured each bogie to the hull, along with torque specifications and installation sequences that prevented misalignment during assembly. Lieutenant General Levin Campbell, who had succeeded Charles Wesson as Chief of Ordnance in May 1942, recognized that documentation alone could not ensure effective field maintenance. Campbell established a comprehensive training program that sent experienced mechanics to armored units before they deployed overseas, ensuring that each tank battalion included personnel who understood Sherman systems in detail. These specialists carried complete sets of technical manuals and were equipped with toolkits specifically designed for Sherman maintenance requirements. The effectiveness of this system became apparent during the buildup for Operation Torch in late 1942. American armored units staged in England reported operational readiness rates exceeding 80%, significantly higher than comparable British formations equipped with more complex vehicles. The difference was not in inherent reliability. Shermans broke down at roughly the same rate as other tanks, but in the speed and effectiveness of repairs. A Sherman with transmission problems could be back in service within hours if replacement parts were available, while a British Churchill might require days or weeks for similar repairs. William Knudsen, now serving as a lieutenant general in charge of production coordination, had ensured that replacement parts were indeed available. The Office of Production Management maintained strategic stockpiles of critical Sherman components at depots throughout the United States and overseas. Standard Nomenclature List G104 cataloged over 15,000 individual parts and assemblies, each with its own supply code and ordering procedures. A maintenance officer in Tunisia could requisition a complete final drive assembly using the same forms and procedures as his counterpart in Kansas, confident that the part would arrive within established timeframes and fit without modification. By January 1944, American factories had delivered over 25,000 Sherman tanks to Allied forces, with production continuing at rates that German intelligence considered impossible. Heinrich Ernst Kniepkamp, analyzing captured American vehicles at German testing facilities, reported to his superiors that American tanks sacrificed individual performance for mass production advantages. His assessment was technically correct, but strategically incomplete. The Americans had not simply chosen quantity over quality, they had chosen systematic availability over individual excellence. The proof of this choice was visible on assembly floors from Detroit to Los Angeles, where identical tanks rolled off production lines with clockwork regularity. Each vehicle carried the same power plant, the same suspension components, the same transmission assemblies, and the same technical manuals. When those tanks reached combat zones, they could be maintained by crews who had trained on identical vehicles using identical procedures. The mechanical complexity that European designers considered essential for battlefield effectiveness had been replaced by systematic simplicity that prioritized operational availability over individual sophistication. Cast iron Charlie Sorensen, watching his latest GAA engine disappear into a Sherman hull, understood exactly what this meant. The tank would break down eventually, they all did. But when it did, any qualified mechanic with the right manual and the right parts could put it back together again. That was not glamorous engineering, but it was winning engineering, designed for the reality of industrial warfare rather than the romance of mechanical perfection. Staff Sergeant Tommy Mitchell crouched beside his disabled Sherman in the Tunisian desert sand outside Kasserine Pass in February 1943, studying the technical manual under the light of a field lamp while his crew prepared to swap out the final drive assembly. The tank had thrown a track during the previous day's engagement, and the subsequent inspection revealed stress fractures in the final drive housing that would have sidelined most armored vehicles for weeks. Mitchell's Sherman would be fighting again by morning. The repair process that Mitchell followed had been designed specifically for this scenario. The Sherman's final drive consisted of three major components: the differential housing, the brake assembly, and the drive sprocket mechanism, all contained within a bolted housing that could be removed as a complete unit. Technical Manual 9-759 provided explicit instructions for this procedure, including the torque specifications for the 16 bolts that secured the assembly to the hull and the proper sequence for disconnecting hydraulic and mechanical linkages. Mitchell's crew had practiced this repair during training exercises in Georgia, but the desert presented new challenges. Sand infiltration required additional cleaning procedures, and the extreme temperature differential between day and night affected bolt tension and hydraulic fluid viscosity. The technical manual anticipated these variables with specific guidance for environmental conditions, ensuring that crews could adapt standard procedures to local circumstances without compromising mechanical integrity or safety margins. By contrast, German armored units operating in the same theater faced fundamentally different maintenance challenges. The Panzer IV tanks that had dominated earlier campaigns were experiencing chronic final drive failures under the stress of extended desert operations. Heinrich Kniepkamp's sophisticated engineering solutions, which had performed admirably during shorter European campaigns, proved vulnerable to the sustained mechanical stress of North African conditions. German maintenance reports from the Africa Corps documented final drive failure rates exceeding 30% among Panzer IV units, with many vehicles requiring complete powertrain rebuilds that could only be performed at specialized depot facilities. The technical sophistication that German engineers considered essential for battlefield superiority had become a liability under operational conditions. Panzer IV Final drives used precision-machined gear sets and complex bearing assemblies that delivered superior performance when properly maintained, but required specialized tools and factory-trained technicians for major repairs. A German tank with final drive problems faced weeks of downtime while awaiting parts and personnel, assuming the necessary resources were available at all. American armored divisions in Tunisia reported significantly different maintenance statistics. Sherman final drive assemblies failed at roughly the same rate as their German counterparts, but the modular design philosophy meant that field crews could complete repairs that would have required depot-level facilities for other vehicles. A Sherman crew experiencing final drive problems could remove the entire assembly in approximately 4 hours using standard tools and install a replacement unit in another 4 hours. The faulty assembly was shipped back to specialized facilities for rebuilding, but the combat vehicle returned to service immediately. This operational advantage became more pronounced as Allied forces moved into Italy during the summer and fall of 1943. The mountainous terrain and poor road conditions placed additional stress on tank drivetrains while limiting access to heavy maintenance facilities. American armored units maintained operational readiness rates above 75% throughout the Italian campaign, while German formations struggled with chronic maintenance backlogs that reduced their effective strength below 50% of authorized levels. Signal Corps photographers documented the reality of Sherman maintenance during the Anzio operations in early 1944. Their images showed American crews performing complex mechanical procedures under field conditions that would have been considered impossible for most contemporary armored vehicles. One photograph captured a complete engine replacement operation conducted in a muddy vineyard using nothing more sophisticated than a portable crane and hand tools. Another showed crews swapping an entire bogie assembly on a Sherman that had struck a mine, with the repair completed and the vehicle back in action within 6 hours of the incident. The engineering philosophy that made these repairs possible reflected Barnes's original insight about the relationship between design complexity and operational availability. Every major Sherman component had been designed as a discrete module that could be removed and replaced without affecting adjacent systems. The power plant could be extracted without disturbing the transmission. The suspension bogies could be swapped without affecting hull integrity. The turret could be removed and replaced without compromising the electrical or hydraulic systems that connected it to the hull. This modular approach required significant compromises in individual component performance. Sherman final drives were heavier and less efficient than their German equivalents, reflecting the additional structural requirements of the bolted housing design. Sherman suspension bogies provided less sophisticated ride characteristics than the torsion bar systems used on newer German vehicles, but they could be manufactured using conventional machine tools and maintained by crews with basic mechanical training. The strategic implications of these trade-offs became clear during the buildup for Operation Overlord in spring 1944. American armored divisions staged in England reported the highest operational readiness rates of any Allied formations, despite having been equipped with vehicles that had crossed the Atlantic under their own power and undergone extensive training exercises. The Sherman's transportability, its ability to fit standard railroad cars, cross standard bridges, and operate from standard landing craft, had proven inseparable from its maintainability. A tank that could reach the battlefield could also reach the workshop, and a tank designed for field repair could be kept in fighting condition under any circumstances. German intelligence assessments from this period recognized the American achievement, but misunderstood its significance. Kniepkamp's technical reports correctly identified the Sherman's performance limitations relative to newer German designs, but failed to account for the operational advantages of systematic maintainability. German planners calculated armor thickness, gun performance, and mobility characteristics while overlooking the fundamental question of how many tanks would actually be available for combat on any given day. The answer to that question was becoming visible across every theater where American armored forces operated. Shermans broke down at predictable rates and were repaired with predictable efficiency, creating a baseline of operational availability that German formations could not match despite superior individual vehicle capabilities. The tank that Barnes had designed to be fixed in a field was proving its worth not through mechanical excellence, but through systematic reliability, turning ordinary maintenance procedures into strategic advantages that accumulated with each day of sustained operations. Captain Robert Hayes climbed out of his burning Sherman near St. Vith in July 1944, his face blackened by smoke and his uniform singed from the flash fire that had erupted in the fighting compartment 3 minutes after a German 75mm round punched through the right sponson. Hayes and his crew had escaped, but the tank was a total loss, consumed by flames that had ignited within seconds of penetration and burned with an intensity that melted steel components and destroyed everything combustible inside the hull. Hayes's experience was becoming disturbingly common among American armored units in Normandy. Aberdeen Proving Ground had begun receiving field reports in May 1944, describing Sherman fires that seemed disproportionately severe compared to other Allied tanks operating under similar conditions. The initial reports were fragmentary and often contradictory, compiled by crews who had survived harrowing experiences and evacuation procedures that left little time for technical analysis. But as the reports accumulated through June and July, patterns began to emerge that demanded systematic investigation. Barnes ordered a comprehensive study of Sherman fire incidents, drawing on combat reports, casualty statistics, and technical examinations of damaged vehicles recovered from battlefield sites across France and Italy. The study team, led by Colonel William McCarthy from Aberdeen's Ballistics Research Laboratory, compiled data on over 400 Sherman losses attributed to fire during the first 3 months of the Normandy campaign. Their findings were both precise and alarming. 68% of Shermans struck by enemy fire experienced catastrophic internal fires, compared to 34% for comparable British tanks, and less than 20% for Soviet vehicles operating on the Eastern Front. The technical investigation that followed revealed the mechanical cause with mathematical clarity. Early production. Shermans used dry stowage ammunition storage, with 75mm rounds stored in vertical racks mounted high in the sponsons on either side of the fighting compartment. These racks placed ammunition at the optimal height for loader access, but also positioned the rounds directly in line with the hull's weakest armor sections. When enemy projectiles penetrated the sponson armor, they often struck ammunition directly, causing instantaneous detonation that killed crews and destroyed vehicles before escape or fire suppression became possible. The problem was compounded by the location of additional ammunition storage below the turret basket, where high explosive rounds were stowed in easily accessible bins that allowed rapid reloading during sustained engagements. This arrangement optimized combat efficiency but created multiple ignition sources throughout the fighting compartment. A single penetrating hit could trigger a cascade of secondary explosions as burning propellant ignited adjacent rounds, producing fires that reached temperatures exceeding 2,000 degrees Fahrenheit within the enclosed hull space. McCarthy's team determined that the fire problem was not inherent to the Sherman design, but rather a consequence of specific stowage arrangements that could be modified without compromising the tank's fundamental architecture. The solution they developed reflected the same modular design philosophy that had governed every other aspect of Sherman engineering. Rather than redesigning the entire ammunition system, they would replace the vulnerable dry stowage with a completely new wet stowage arrangement that isolated ammunition from potential ignition sources. The wet stowage system relocated 75mm rounds from the high-mounted sponson racks to new storage bins positioned low in the hull, below the turret basket, and surrounded by water-filled jackets. Each storage bin was constructed as a sealed unit containing both ammunition and a water reservoir designed to absorb heat and suppress combustion in the event of penetration. The water jackets were pressurized to ensure rapid distribution of coolant around stored rounds, and the entire system was designed to contain fires rather than prevent them, recognizing that any ammunition storage would remain vulnerable to direct hits. Engineering tests at Aberdeen demonstrated the effectiveness of this approach with controlled experiments that simulated combat penetrations. Dry stowage Shermans subjected to simulated hits experienced fires in 82% of test scenarios, with flames reaching lethal intensity within 30 seconds. Wet stowage prototypes showed fire rates of only 14% under identical conditions, and those fires that did occur burned at much lower temperatures and could often be suppressed using standard fire extinguisher systems. The challenge of implementing wet stowage modifications reflected the scale and complexity of American tank production by mid-1944. Over 30,000 Shermans were already in service with Allied forces, and production was continuing at rates exceeding 800 vehicles per month across multiple contractor facilities. Retrofitting existing tanks required field modification kits that could be installed by maintenance crews without returning vehicles to depot facilities, while new production had to be modified without disrupting assembly schedules or parts supply chains. K.T. Keller coordinated the implementation from Detroit, working with Barnes and Campbell to develop retrofit procedures that utilized the Sherman's modular architecture. The wet stowage conversion required removal of existing ammunition racks, installation of new storage bins, and integration of water circulation systems, but the work could be completed using standard tools and documented procedures similar to other Sherman maintenance operations. Field modification kits began reaching combat units in August 1944, with complete retrofits typically requiring 12 to 16 hours of work by trained maintenance crews. Simultaneously, production lines at Detroit Tank Arsenal, pressed steel, and other contractor facilities began incorporating wet stowage into new vehicles. The modification required new tooling for ammunition bin fabrication and additional quality control procedures for water jacket testing. But the changes integrated smoothly into established assembly processes. By October 1944, all Shermans leaving American factories incorporated wet stowage as standard equipment. The results of this systematic response became measurable within months of implementation. Combat reports from late 1944 showed Sherman fire rates dropping to 15% among units equipped with wet stowage modifications, closely matching the test results obtained at Aberdeen. Crew survival rates improved correspondingly, with fewer total losses and more opportunities for vehicle recovery and repair after combat damage. The wet stowage modification represented more than a technical fix. It demonstrated the institutional capacity for rapid improvement that Barnes had built into American armor development from the beginning. The same modular design philosophy that enabled field maintenance also enabled field modification, allowing systematic problems to be addressed through engineering solutions rather than doctrinal adjustments. American tanks could be improved in production and updated in service, creating a continuous cycle of enhancement that kept pace with evolving battlefield conditions. This was not glamorous engineering, nor was it the kind of breakthrough innovation that captured headlines or impressed foreign observers. It was systematic problem-solving applied to the realities of industrial warfare, where the ability to identify, analyze, and correct deficiencies often mattered more than initial technical superiority. Major General Barnes walked the production floor at Fisher Body Division in Grand Blanc, Michigan, in September 1944, inspecting the first M4A3E8 Sherman to roll off the assembly line with its revolutionary horizontal volute spring suspension system. The new HVSS configuration replaced the vertical spring bogies that had served adequately for 3 years with a wider track system and improved road wheels that promised to transform the Sherman's battlefield mobility without compromising the maintainability principles that had guided its original design. The E8 modification represented the culmination of Barnes's systematic approach to armor development. Rather than designing an entirely new vehicle to address the Sherman's limitations in firepower and protection, American engineers had chosen to evolve the existing platform through modular improvements that preserved its fundamental maintenance advantages. The HVSS system used the same bolt-on attachment philosophy as the original VVSS bogies, but incorporated torsion bar elements and wider 23-inch tracks that distributed weight more effectively and provided superior ride characteristics on rough terrain. Technical Manual 9-781, published specifically for HVSS-equipped Shermans, demonstrated how the new suspension integrated seamlessly with existing maintenance procedures. The manual's suspension section showed crews how to remove and replace HVSS bogies using the same tools and techniques they had learned for VVSS systems, with only minor modifications to accommodate the new components' different dimensions and weight distribution. A crew trained on standard Shermans could service an E8 with minimal additional instruction, preserving the institutional knowledge that had made American armored maintenance so effective. The first E8 Shermans reached European combat units in October 1944, where their improved mobility immediately impressed crews who had grown accustomed to the harsher ride characteristics of earlier models. Staff Sergeant Mitchell, now commanding an E8 in Lieutenant Colonel Crichton Abrams' 37th Tank Battalion, reported that the new suspension allowed sustained high-speed movement over terrain that would have damaged standard Shermans. More importantly, from Barnes's perspective, the improved suspension reduced mechanical stress throughout the drivetrain, decreasing maintenance requirements and extending component service life. By war's end in May 1945, American factories had produced over 49,000 Sherman variants across all models, creating a global inventory of standardized armored vehicles supported by comprehensive documentation and interchangeable parts. The M4 family had achieved Barnes's original objective. Availability had proven more strategically valuable than individual excellence. American armored divisions had maintained higher operational readiness rates than any comparable force throughout the war, not because their tanks were mechanically superior, but because their tanks could be kept running under any circumstances. The long-term validation of this philosophy became apparent in the decades following the war's conclusion. Sherman tanks continued serving with Allied nations well into the 1970s, with many vehicles accumulating over 30 years of active service through systematic maintenance and component replacement. The modular design that had enabled rapid wartime repair also enabled peacetime modernization, as nations updated their Shermans with new guns, improved armor, and modern fire control systems while retaining the basic hull and drivetrain components. Israel's experience with Sherman modernization provided the most dramatic example of the design's inherent adaptability. Israeli engineers completely rebuilt hundreds of surplus American Shermans during the 1950s and 60s, installing French 75mm guns, upgraded power plants, and improved armor packages while preserving the fundamental maintenance characteristics that made the vehicles sustainable for a resource-limited military. These modified M50 and M51 Shermans served effectively into the 1980s, demonstrating that Barnes's original engineering philosophy remained relevant 4 decades after the initial design decisions. The ultimate testament to Sherman maintainability came from Paraguay, which operated 3 M4A3 E8 tanks until December 2018, 77 years after the first Sherman rolled off Detroit production lines. These vehicles, originally manufactured in 1945, had been maintained in operational condition through 7 decades of service using technical manuals, spare parts inventories, and repair procedures established during World War II. The fact that Sherman tanks could remain functional well into the 21st century using mid-20th century maintenance technology validated Barnes's fundamental insight about the relationship between design simplicity and operational longevity. The contrast with contemporary armored vehicle maintenance illuminated the philosophical differences between Barnes's generation of engineers and their modern successors. The M1A2 SFV3 Abrams tank that had become America's primary battle tank by 2018 represented the pinnacle of armored vehicle technology, incorporating composite armor systems, digital fire control, and turbine propulsion that delivered battlefield capabilities unimaginable during World War II. The Abrams could engage targets at ranges exceeding 4,000 meters with first-round hit probabilities above 90%, while surviving direct hits from projectiles that would have destroyed any Sherman variant. But the Abrams achieved this performance through systematic complexity that fundamentally altered maintenance requirements. The tank's turbine power pack could be removed and replaced rapidly using hydraulic lifts and specialized tooling, but diagnosing engine problems required computerized test equipment and technicians trained in gas turbine systems. The digital fire control system enabled unprecedented accuracy and target engagement speeds, but failures required line-replaceable units manufactured to aerospace tolerances and diagnostic procedures that demanded intimate knowledge of embedded software systems. Modern tank maintenance had evolved from Barnes's wrench logic to what contemporary engineers called tester logic, systematic approaches that achieved higher performance through increased complexity, but at the cost of accessibility to non-specialist maintainers. An Abrams could be serviced efficiently and effectively, but only by crews with specialized training using equipment specifically designed for that vehicle family. The institutional knowledge and universal tools that had made Sherman maintenance possible in any workshop with basic capabilities had been replaced by technical specialization that required dedicated facilities and manufacturer support. This evolution reflected broader changes in military technology and industrial capability, but it also highlighted the strategic significance of Barnes's original design philosophy. The choice to prioritize maintainability over sophistication had created a weapon system that remained useful across multiple generations of technological change, serving effectively in conflicts and peacekeeping missions long after more advanced contemporary designs had been retired to museums. The Sherman's enduring legacy was not mechanical elegance or battlefield dominance, but systematic availability that translated engineering decisions into strategic advantages measured in decades rather than battles. Barnes had designed a tank that could be fixed anywhere by anyone with the right manual and the right parts, and that capability had proven more valuable over time than any individual performance characteristic.